Hello, in this video we're going to take a look at classification of continuous time signals. So one of the properties of signals that we're often interested in is its size. How do we measure the size of a signal? Well, there are different ways to measure the size of a signal. So let's say we have a signal x of t. One measure for its size is given by signal energy, or denoted E sub x. E sub x is given by this integral. It's the integral over all of time of the magnitude of x of t squared. So if x represents voltage, then we can think of E sub x as giving the energy that's dissipated across a 1 ohm load. Now if E sub x is finite, then we say that our signal x of t is an energy signal. In order for E sub x to be finite, x of t necessarily has to go to 0 as t goes on to infinity. So what happens if we have a signal x that does not satisfy this property? As an example, what happens if we have a periodic signal? In this case, we cannot calculate the energy, so we need to use another measure for its size. In this case, we can make use of what's referred to as the signal power, denoted P sub x. P sub x is given formally by the following expression. It's the integral over an interval of time, capital T, of the magnitude of x of t squared. We divide that integral by our interval of time, capital T, and if x is not periodic, then we take the limit as t goes to infinity. So P sub x can be interpreted as the time average of the instantaneous signal energy as you let the averaging interval grow unbounded. Of course, if x of t is a periodic signal, then you do not need this limit at all. Now, P sub x is also referred to as the mean square value of x, and the square root of P sub x is sometimes referred to as, or is often referred to as, the root mean square value. Now, if you have P sub x, the power of the signal, being a finite non-zero value, then x of t is referred to as a power signal. Note that a signal cannot be both an energy signal and a power signal at the same time. Again, a classic example of a power signal is a periodic signal. So let's take a look at a couple of examples. First, we want to determine whether the signal shown over here, x of t, is an energy signal or a power signal. So what we can note is that x of t in this example goes to 0 as t goes to infinity. So that immediately suggests that we can make use of the definition for the signal energy. So E sub x is going to be the integral from minus infinity to infinity of the magnitude of x of t all squared dt. Now our signal in time is divided into two intervals. It's the integral from minus 1 to 0 of 2 squared dt plus the integral from 0 to infinity of our signal 2e to the minus t over 2 all squared dt. The first integral here just winds up being equal to 4. The second integral here winds up being equal to 4 times the integral from 0 to infinity of e to the minus t dt. And this integral here works out to being equal to 1. So we can then get that our total signal energy, E sub x, is simply going to be 4 plus 4, or 8. Here's another example. X of t is shown in the following curve. In this case, we can see that our signal is going to be periodic. So, in particular, we have a signal x of t that's periodic with period over here, with a period of 2. So x of t is periodic. And if we have a periodic signal, we can make use of signal power. So P sub x is equal to 1 over our period t, integral over our period of our magnitude of our signal squared. Now in this case, the period is equal to 2. So this is a half. The integral over the period. So I could take my limits of the interval, let's say going from minus 1 to 1. And my signal in this case is simply given by t. So I'm going to have t squared here, dt. And so this is a half t cubed over 3 taken from minus 1 to 1. And this basically works out to 2/3. So I have 1/3 here for my signal power. Now again, just note, because I had a periodic signal, I did not have the limit in the expression for the signal power. As another example, let's consider a harmonic signal. So a harmonic signal in this case is given by c cosine omega naught t plus theta. It's actually a periodic signal, so I can make use of the power and hence calculate also the RMS value for the signal x of t. So we have an amplitude c, the frequency omega naught, and some phase term. If I want to calculate the power for this signal, I'm going to have P sub x is going to be equal to 1 over period t naught, integral over that period t naught of the magnitude squared. So in this case, it's going to be c squared cosine squared over omega naught t plus theta. Now, t naught, the period, is the period of our original harmonic signal omega naught. So t naught is 2 pi over omega naught. So let's work out this integral. But before doing that, I'll just draw your attention to the cosine squared term. I could rewrite this as being equal to 1/2 plus 1/2 cosine of 2 omega naught t plus 2 theta. So this is a simple trigonometric identity. So my signal power is then going to be equal to 1 over t naught, or I could actually write c squared over t naught, the integral over t naught of 1/2 plus 1/2 cosine 2 omega naught t plus 2 theta, all of this dt. Now, the first part of the integral, with the half term here, is simply going to work out to giving me c squared over 2. And for the second part of the integral, I'm going to have plus c squared over 2t naught, the integral over the period t naught, of cosine 2 omega naught t plus 2 theta dt. Now, if I were to plot this function, okay, I would have cosine that looks like this. Now, what do I have for the value of t naught? Well, this is the period that's associated with my original harmonic signal, the cosine omega naught t. The period of this cosine function is actually the frequency is 2 omega naught, so the period would be t naught over 2. So if I look at my cosine function that's plotted over here, I'm actually going to be integrating this over a period of t naught, which is illustrated over here. So in other words, I actually have 2 cycles of this cosine function fitting within my original period t naught. The point being, though, if I integrate this cosine function over the period t naught, I'm going to have an equal amount of area under the curve that's positive and an area under the curve that's negative. So in other words, this integral here is going to integrate out to 0. In fact, any time you wind up integrating a cosine function over a period or an integer multiple of the period, you wind up getting 0. So the power then of my signal is simply going to be equal to c squared over 2, or if I look at the root mean square value, the root mean square value is the square root of p sub x, which is simply c over the square root of 2. Let's take a look at another example. In this case, I want to determine the power and the root mean square amplitude of a complex exponential signal. So it's a complex exponential signal. It's also a periodic signal. So to do that, again, I could write that the power, the signal power, is given by 1 over t, the integral over a period. And in this case, if my frequency is omega naught, I can use period t naught. And I have to find the magnitude of d e to the j omega naught t all squared dt. And this simply works out to 1 over t naught, integral over the period t naught of d squared dt, or simply d squared if d is a real number. D represents the amplitude. So p sub x is d squared, and then the root mean square value, which is the square root of p sub x, is simply the amplitude d. Okay. So these examples illustrate how we can determine signal energy or signal power if, in particular, in the latter case, the signal winds up being periodic. So another way we can classify signals is in terms of their symmetry properties. We can make use of what are referred to as even and odd signals. So in particular, if a signal is even, x of t is equal to x of minus t. We can also characterize that as saying that the signal is symmetric. X of t is odd if x of t is equal to minus x of minus t. Sometimes we call that an antisymmetric signal, or a signal that exhibits odd symmetry. Just as an example over here, a very simple way of looking, or is a very simple example of an even x of t is a cosine function. So your cosine function, we know, exhibits symmetry about the real axis, and so cosine of t would be an even signal. On the other hand, if we have an odd x of t, right, sine is actually a good example. And we often know, or we often see, or refer to the sine function as exhibiting odd symmetries. So the origin acts as a point of inversion symmetry. So let's take a look further and note that any arbitrary signal x of t can always be expressed as a sum of an even component and an odd component. The even component is given by a half x of t plus x of minus t, and the odd component is given by a half x of t minus x of minus t. So let's take a look at an example. We're given a signal x of t over here, cosine t plus sine t, and we want to find the even and the odd parts. Well, by inspection, I think you can see that cosine of t would form the even part of the signal, sine of t would form the odd part of the signal. But let's actually verify this using the definition of an even part of a signal and the odd part of a signal. So, we start with x of t equal to x e of t plus x o of t. The even part of this signal, x e of t, is a half x of t plus x of minus t. And in this case, we have cosine t plus sine t plus cosine of minus t plus sine of minus t. So this is a half cosine t plus sine t. Cosine of minus t is cosine t. Sine of minus t is minus sine t. So I'm going to have the sine t terms knocking out. I'll have 2 cosine t, a half of that. So I'm left with x e of t is cosine of t. If I take a look at x o of t, x o of t is a half of x of t minus x of minus t. So in this case, it's a half cosine of t plus sine t minus cosine of minus t minus sine of minus t. So that's cosine t plus sine t. Cosine of minus t again is cosine t, so I have minus cosine t. And then sine of minus t is minus sine t, so minus sine t is plus sine t. So the cosine terms vanish. I'll be left with 2 sine t, half there. So I'm left finally with sine of t. So you can see that by calculation through the formal definition of the xo of t, I get sine of t. By calculation of the formal definition of xe of t, I get cosine of t, which is exactly what I would be able to identify in terms of identify directly by inspection. So if you have any questions, send me an email.